Hello there, this is Jude Socrates. Welcome to video number 34 for my series in multivariable calculus. This is known as Math 5C at Pasadena City College. So today is a happy day. We are going to study the last kind of integral that we are going to see in this course. So it is once again a surface integral, just like the one that we saw in our last video. But this time, the function that we are integrating will be a vector field, not a scalar function. So we're going to find what is called the flux integral of this vector field through what is called an orientable surface. So all of that will be explained in just a little bit. I will see you on page 285. All right, here we are. So the notation for the flux integral is once again a double integral over the surface S. We have this time a vector field in x, y, and z. But instead of just times ds, that's a dot product. Okay, you're not seeing things. That's a dot product, and there is an arrow over the s. Okay, so of course all of that will be explained in a little bit. But what we're going to start with now is who is this s? Okay. So that's not just any kind of surface. It has to be what is called an orientable surface. But fortunately, all the surfaces that we have been looking at so far are orientable. So what is the definition of an orientable surface? So a surface is orientable if every point on S has a unit normal vector, which we will write as n of x, y, z, such that the function n of x, y, z is continuous. Okay? Well, what does it mean for a vector function to be continuous on a surface? Well, n is already a unit normal vector, so the length is not going to change. Okay? So what could change with a vector now? Its direction. Okay? So we want a choice for the normal vector, which will not suddenly change direction on us. Okay? So to do that, we're going to need a unit vector. Okay, so I am going to borrow Hagrid's pink umbrella, okay, and that is what we are going to use for our unit normal vector. Okay, so let's start with a plane or a triangle, okay, any flat surface in space. Okay, so what would the normal vector look like? Well, we already know what the normal vector to a plane should look like. Okay, it should be perpendicular to the plane. So we want a continuous function. So basically, we just have to pick the same unit normal vector everywhere on the plane, everywhere on this triangle. Okay, so in this case, I've chosen the unit vector which is going up, but I could also choose the unit vector which is going down. Okay, so both of those are valid choices. All right, one is not any better than the other. Okay, however, as soon as you pick one, you have to stick with it for the entire surface. Okay, so if I choose the downward normal unit normal vector for this triangle, I can suddenly change my mind and say, oh, I'd rather go up for the rest of the triangle. No, you have to pick one and stick with it. All right, so if you have this plane, for example, 2x minus 6y plus 3z is 12. Okay, we know that the normal vector is 2 minus 6, 3. How long is this vector? 4, 36, 40 plus 9, 49. Square root of 49 is 7. Okay, so we have two choices for our normal vector. We can take 1/7 of this vector or negative 1/7 of that vector. Okay, so I switch the sign for that vector in our second normal vector. Unit normal vector. Okay, so that tells us that if you do already have one choice for an orientation, this continuous normal vector, you could also take the entire negative of that orientation. So both are valid unit normal vectors for your surface, but you have to pick only one. Okay, what about spheres? Okay, so here's my pseudosphere. And there you go. I lost the umbrella. So if you are somewhere on the sphere And since in this case this is a solid ball, I don't have a hollow ball on me, you can take as your normal vector the outward pointing normal vector. Okay, so sometimes it's pointing up, sometimes it's sideways, sometimes it's pointing down. Okay, so one adjective that will apply to all of those points would be outward facing normal vector. Okay, so we actually saw this in our last section, our last video, where we found this vector after taking the cross product of the two partial derivatives. Okay, and we discovered, oh, it's actually already a unit vector. Okay, so if you plot some of those vectors for various values of phi and theta, you will get these outward facing normal vectors. Okay, so in general, that is how we are going to find these normal vectors. We're going to take the partial derivatives of our orientation, and we're going to take their cross product, but that may not be a unit vector, so we will divide by its length because we are supposed to be given a smooth surface. So the length of this cross product should not be 0, should not be the 0 vector, so we can construct this unit vector. Okay, now earlier we called it n of x, y, z. Okay, but because our surface is controlled by u and v, we will also use the notation n of u, v. Okay, now we also looked at Cartesian surfaces where, let's say, z is a function of x and y, and we said that the cross product of gx and gy is minus gx minus gy 1. Okay, so to make that unit vector, we divide by the length. So we square the two partial derivatives and we add 1. Okay, so in this case, that's a positive 1. This vector is always pointing upward. Okay, but it might tilt a little bit. The z coordinate of that vector is always positive 1. Okay, so suffice it to say that every surface that we are going to give you in any of the problems will be orientable. Okay, maybe it's a plane, maybe it's a sphere. Okay, in the example that we're going to work on later, maybe it's a cylinder. Okay, so what about a non-orientable surface? Okay, so I'm going to spend just maybe 5 minutes or so talking about the Mobius strip, because I actually had some fun writing up the next 4 or 5 pages. Okay, I found some information on the web, lots of good stuff there if you know how to look. And let me show you. Okay, so first of all, what if you want to create a Mobius strip just by hand? Okay, so here's a strip of paper. Okay, don't worry about that. It's just scratch paper. If you connect the two ends of this strip of paper, you will just get an ordinary looking cylinder. Okay, a very large ring. Okay. However, here's how you make a Mobius strip. Okay, instead of just connecting the two ends like that, you will take one end and give it half a twist. Okay, and now attach it to the other end. Okay, so that is your Mobius strip. Okay, so I'm going to pause the video. I'm going to tape these two ends together. All right, so there you go. That is your Mobius strip. And yeah, if you're watching this at home, take a strip of paper and make one of your own. Okay, so why is this not an orientable surface? Okay, you can already see that it's kind of twisting around in space. Okay, so that gives us a clue. Okay, so here's how we show it. Okay, we're going to do it in 2 ways. Okay, we're going to do it on paper and we're going to do it in GeoGebra as well. Ooh, it's going to be fun. The point here is that a surface is supposed to be infinitely thin. Okay, it's not supposed to have any thickness at all. Okay, so this is of course paper thin. Okay, so what does that mean? There is no up, there's no down, there's no top, there's no bottom, there's no left, there's no right. Okay, so I'm marking one point on the Mobius strip right there. Okay, and I'm also going to mark the other side. Okay? Because as I said, there's no front, there's no back, there's no top, there's no bottom. That point is exactly the same as that point. Okay? There is no front, there is no back. That is one point. Okay? However, we're going to have a problem with continuity. Okay? And here's why. And here's how I'm going to show it to you. Okay? I will mark one side, one of the dots. Okay? So I'm just going to put the letter A over here. Okay? So that has the letter A. That's the same dot in the back, but it doesn't have a letter A. Okay? So where is Hagrid's umbrella? Okay, so right here. Okay? We have to choose a unit normal vector for every point. Okay? So let's say at point A, we're going this way. Okay? So notice that I'm on the side that has the A on it. Okay? Although once again, that point and this point are exactly the same point. Okay? And that's what's going to mess us up in just a little bit. Okay? So here's what we're going to do. We're going to need a unit normal everywhere else on the surface. Okay? I'm just going to go down the middle. Okay? And of course, anywhere there, I can just go left and right and it will still be continuous, correct? Okay. So now, I'm going this way. I'm going this way. And now my hands are tired. Now I need to grab it from over here. Whoops. Okay, so I'm pointing down, not cheating you. Okay. And then I keep going. Okay, and now I'm over here. And I'm working my way back to the black point over here. And check it out. I'm now on that side. Okay. The marked side is over here. Okay. So I started out with the umbrella pointing this way. And when I got back over here, it's now pointing in the other direction. Okay. So that's bad because points over here will be pointing that way, but points over here will be pointing the other way. That's not continuous. Okay. You suddenly change direction. Okay, so here's the part I'm really excited about, even though we're not going to do any calculus on the surface at all. It was just a fun thing to do. Okay, so I found some stuff on the internet about how to make a Mobius strip, except they basically just gave you the answer. Okay, what's the fun in that? Okay, when it's more fun to ask, okay, how did you get there? How did you make that? Okay, so remember when we created the helicoid? Okay, so we basically walked on a helix, okay? And as we walked, we carried a baton and it turned around with us, okay? So yeah, and I said you can make one by walking on a straight line, and then you turn the baton as you walk, okay? So, we're going to use that same idea, except instead of walking on a straight line, we are going to walk around a circle, okay? And we're going to start with the baton centered at 1, 0, 0, and it's going to be vertical, okay? It's going to be pointing up and down, okay? Let's go to GeoGebra and show you. Okay, so here's what we're going to do. We are going to use this slider, okay? And as we walk around the unit circle on the XY plane, we are going to turn the baton around so that when it gets back to where we started, it's going to be upside down, okay? So remember how when we made that Mobius strip, instead of attaching the edges like this, I gave it a half twist, okay? So this is the equivalent of making that half twist. Okay, so I'm going to play the slide off. Here we go. Turning, turning, turning. And as we reach pi, which is over here, notice that the center stays on the circle. It's now lying on the negative x-axis. And then it's turning again. It's keeping on turning. And look at now how the red bottom half is pointing up. Okay, it's going to go backwards. Okay, reverse the video, and it's going to be lying down again on the negative x-axis. You hear the bird? There's a family of birds nesting outside my window. They're so happy. So here it is at the beginning where the blue part is up. Okay, so as I mentioned, I go like 4 or 5 pages deriving how to make the surface command for this Mobius strip, but it's right here. So let me show you. There is your Mobius strip in GeoGebra. Ooh, ah. So let's play the slider again, and we can see how. So look, blue on top, red on the bottom. Okay, as it turns around, see how it stays on that Mobius strip, and it's now lying horizontally on the x-axis, and it keeps on going. Okay, I'm going to stop it now because what I want to show you is the unit normal vector. Okay, Hagrid's umbrella, which I seem to have misplaced again. So that vector is found, where are you? Segment, where is my vector? Found it, it was right beneath my slider. I think I'm misplacing everything today. So here is, maybe I should shrink this a little bit. Here is the starting point of the baton, and here's the normal vector at that point. Okay, so it's pointing away from the, what you might call the inside portion. So let's see what happens to that normal vector as it turns around, and maybe we should orient that. Okay, there you go. That's a good view. Okay, play the video. Okay, so continuous, continuous. Okay, so that normal vector is just turning. And of course, as we get to the negative x-axis, it's now pointing up. Okay, and it's going to keep going, and it's going to keep going. Remember, it started out pointing towards the positive x-axis. Check out what is happening. It is now pointing towards the negative x-axis. Okay, so again, that's bad because these unit normal vectors will be pointing this way, but there are some points nearby where the normal vector is pointing in the opposite direction. Okay, so just because this is 0, this is 2 pi, doesn't mean they're far apart. No, when you're at 2 pi, you're back where you started. So you're very close to your starting point. Okay, and that is how you violate the continuity of this normal vector. Right, so now finally, let's talk about the flux integral over an orientable surface. Okay, as I mentioned, I think I mentioned that the flux integral is supported in physics because you look for the flux of the electromagnetic field through a surface. Okay, and we have Maxwell's equations that relate things about the electric field, the magnetic field, and so on through these flux integrals. Okay, again, I'm not a physicist, so I'm basically just saying words that I really have no clue what they really mean. Okay, just kidding. Okay, so some of you might not take physics at all, and for that I apologize because you're basically learning something that is not going to be used anywhere in your future classes. But here's something that everyone can relate to, and that is water in the form of rain. Okay, so when you hear the word flux, you might say, oh, did you say flush? Flush the toilet? Yeah, it's really the same root word. Okay, you have fluid, flux, flow. Okay, so how is the rain going to flow? It is going to flow through a hole in the roof. Okay, so let's say we have a flat roof. Okay, let's say you have an ordinary building, like maybe a mini mall, which has a flat top, and someone left a hole in the roof. Okay, so water is going to flow through that hole. Okay, and it's going to make a mess inside that building. Okay, now, of course, there's all kinds of rain. Okay, there are some light showers, okay, so that hardly any water is flowing down, kind of like what we have in Southern California. Or you have really pounding rain, okay, maybe places in the south where you get a lot more humidity, okay? And then there's tornado country where there's wind involved, okay? So not only can you have strong and light rain, but the direction that the rain is falling can also change, okay? And you can walk a little bit, and where you are now is going to be experiencing a different kind of rain as where you were a minute ago, okay? So, if it's falling through a flat hole, then you basically take the amount of rain, which we can express in the unit of kilograms per unit time, in seconds, let's say, per unit area, and then multiply it by the area that it is falling through, okay? So if you multiply by area, that part cancels, and you have kilograms per unit time, okay? How many gallons per minute is falling through that hole, okay? And hopefully you can keep up with it and throw all that water out. Okay, but now, what if your hole through the roof is not perfectly horizontal? Okay, so what if it's slanted now? Okay, so what if it's making an angle of theta with respect to the horizontal? Okay, that hole, I think I forgot to mention, that hole is 1 by 1, a square. Okay, so if it's slightly tilted, the width, would that be the width? No, that would be the length. It's still going to be 1, but now the width will be narrower. Okay? And of course, trigonometry will tell you that that width is now cosine theta. All right? Because that hypotenuse is 1. Okay? So therefore, the amount of rain flowing through is not just this amount, but that amount times cosine theta. Ooh, where have we seen cosine theta before? Okay, but now here's another way to look at the same situation. Okay, the rain is falling down vertically. Okay, this hole, when you look at it through the side, through its edge, is making an angle of theta with the horizontal. Okay, so what do we have here? Since F is vertical, that's a right triangle. Okay. Ooh, I have another vector here. N. Where have we seen N before? Normal vector. Okay. So this is the normal vector, the unit normal vector to that plane. Why is that theta? Okay, simple. It's geometry. Normal means it's making a right angle with respect to this edge. That's the line segment. Okay. So this is also a right angle. But if that is theta, and that's a right angle, this is the complement of theta. Okay, but wait a minute. This is also a right angle, so this angle here is the complement of theta. Ooh, we're back to theta. Okay, so that angle really is theta. F is making an angle of theta with respect to the normal vector to that hole. So, where have we seen cosine theta before? Dot product. Okay, so therefore, if we multiply F by cosine theta, okay, which is the magnitude of our force, we can include the normal vector, the unit normal vector n, into that expression because the length of the unit vector is 1. Okay, now that's important because once we see this, that's just the dot product of F with n. Okay, so therefore the flux passing through that hole when it's edgewise, when it's slanted rather, is just the dot product of your vector field with the normal vector. All right, so that is for a 1-by-1 square. So in general, if you have a hole which has area A, then you multiply that flux by the area that is passing through. Okay, of course, the bigger the area, the more of that rain is going to fall through. Okay, so now we can conceive of the flux integral of a varying vector field across the orientable surface S. Okay, so we need it to be orientable because we're taking this dot product with the unit normal vector. And whenever you integrate, everything has to be continuous. Okay, there's no guarantee that your integral will be defined or will converge if your function is not continuous. Okay, so what are we going to do? Something similar to what we saw in the last video. We're going to take a parametric surface. We have a parametrization for it. We're going to cut up the parametrization to little rectangles that will result in these little patches. Okay, we are going to look at each patch and do what we did over here. Okay, we're going to take the vector field, which we will assume is constant on that patch, and then we'll take the normal vector to that patch. How are we going to get it? Cross product multiplied by the area of that patch. Oh wait, we've done that before. That's the length of that cross product. Okay, so something nice is going to happen. Okay, so here's the derivation. Okay, we have our domain for u and v. We cut it up into small rectangles, and then we find the area of the corresponding patch to this rectangle. We did it in the last video. It's the length of the cross product times delta u delta v. But the unit normal vector at that same corner is the cross product of the two partial derivatives divided by the length. Okay, so when you multiply this by the area, okay, notice that the lengths cancel. Okay, so that pesky square root is going to go away. Okay, so here's the formula for the flux of F through one little patch. We plug in the parametrization into F. We take the unit normal vector, which is over here, and we multiply by the area of the patch. We take the dot product of those two vectors. Okay, so as I said, these lengths are going to magically cancel out, and so we just have the dot product of the force, where you plug in the parametrization, times the cross dotted with the cross product, times delta u delta v, as usual. So that is what we add up in our Riemann, double Riemann sum, and this is the final formula for our flux integral. There is no length involved. Okay. If you don't have a rectangle, then you can just use a type 1 or a type 2 integral, just as we have before. If you have a Cartesian surface, the normal vector, the cross product, was just minus gx minus gy 1, as we saw before. Okay, so earlier I said, okay, there's an arrow on top of the s. What the hell does that mean? It basically just means ds multiplied by the unit normal vector at that point. All right, so here are basically the steps to construct this flux integral. It should remind you of the integral that we used to compute the work performed by a vector field as it moves a particle through a curve. Okay, first you have to start with a parametrization for your surface, and then you plug in that parametrization into your vector field. into P, into Q, into R. Okay, so everywhere there is X, you replace with X of UV. Everywhere there is a Y, replace with Y of UV. Okay, then you get the partial derivatives and take their cross product. Okay, check it's not the zero vector. It won't. Everything we give you is smooth. Okay, we do not find the length of that vector this time. Okay, we just take the dot product of that cross product with the vector field where we have plugged in the parametrization. Okay, that is our integrand. Write down your integral, find your limits, integrate, end of problem. All right, I'll walk you through this example because spheres appear all the time, and then we'll work on the new problem in our work area. Okay, so we saw how to parametrize a part of a sphere using spherical coordinates, and this time, if your center is not the origin, no big deal. Okay, so if your center is at 2, -3, -1, and the radius is 4, you start out with spherical coordinates, the conversion formulas, and then you just adjust. You add 2, subtract 3, subtract 1. Okay, that's your parametrization. We want the right half of the sphere. Okay, so therefore, phi will still go from 0 to pi, but theta will only go from 0 to pi, not all the way to 2 pi. Okay, so that is our right half. We're just looking at it from a different perspective here. It's not on the left, it's still on the right. We want to find the flux of this field. Okay, so we have negative z, 3x plus 1, y minus 2. Okay, so z is this, so we take the negative. X is this, so we multiply by 3, add 1. Y is this whole thing, so we subtract 2. Simplify, we get that as our vector field in terms of phi and theta. Okay, we already know that the cross product of r phi and r theta is this mess, but we know that the radius of our sphere is, I believe, 4. Okay, but also, even though we shifted the center, the cross product stays the same, because when you take the partial derivatives, those constants go away. Okay, so the cross product is exactly the same. We don't get the length. We take the dot product of these two vectors. Okay, so of course the 16 sine phi, we can just leave it out. You have to be told the orientation of the surface. So we will make the normal vectors point to the right. Okay. So if you just check one point, the rightmost point of this right half, you will get it to be 16 times 0, 1, 0. So it is pointing to the right. Okay. If you were told that you want the leftward facing normals, then you take the negative. Okay. Big deal. The only thing that changes is the sign of the final answer. Okay. So when you take the dot product, okay, so multiply in pairs. So this gets multiplied to this gets multiplied to this, and this gets multiplied to this. You can leave the 16 sine phi out for a little bit, okay? But instead of distributing this horrible looking mess, we're going to plan ahead, okay? So check it out. There is a cosine theta here and a cosine theta sine theta here, and a sine theta there, and a sine theta over there, and a constant over here. Okay, if you distribute this part out, there is no theta there. Okay, so here's a smart thing to do. Okay, integrate those thetas first. Okay, so these are the terms that I said you will find. we're going from 0 to pi. Integrate cosine. Oh, you get 0. Nice. So that entire first term goes away. Integrate cosine theta, sine theta. That is also a 0. Excellent. But sine theta, not so lucky. You're going to get 2. Okay, and of course, constant does not go away when you integrate. You're going to get pi minus 0. You're going to get pi. Okay, so once you do that, that expression that we're supposed to integrate is a lot tamer. Okay, all the thetas are gone. We're now only going to integrate with respect to phi, and you know exactly what to do. Okay, so make sure that you include the sine phi everywhere. Okay, we know how to integrate all of those. Final answer, 112 pi. Okay, so let's go to our workroom and let us find the flux on a different kind of surface. Okay, fresh problem. We want to find the flux of this vector field, xz plus 1, y squared plus z, 3x minus y. We want the flux across the front half of this cylinder, which is the part which is between 2 and 5, with forward-facing normal vectors. Okay? So earlier we did the right half, and I wanted rightward-facing normal vectors. So now how about the front half, and we want forward-facing normal vectors. Okay, so first we need a parametrization. Okay, it's not given to us, so we have to make it ourselves. We know how to do a circle. We know how to do an ellipse. Okay, so let's assemble our parametrization using polar. Okay, we will have 4 cosine of u. X is 4 cosine of u. Y is 3 sine of u. Okay, so now we're on this ellipse, but z is going between 2 and 5. So we're just going to put z in the last coordinate. And of course, u is going from element of, u is from 0 to 2 pi. Oh, wait. Oh, wait a minute. We only want the front half of this elliptic cylinder. Okay, so we're going from, so it's the y coordinates. Okay, we have to think about. So y is going from negative to positive. So your angle should go between negative pi over 2. Oops, I thought I was in GeoGebra. Negative pi over 2 and positive pi over 2. And our z has to go from 2 to 5. Okay, so that's good. That is our parametrization. Let's go to GeoGebra and see if we are right. Okay, looks like we got it. So here is our cylinder. We only take the front half. Okay, so here's our positive x-axis. We're going from negative y something to positive y something. Okay, and z is only going between 2 and 5. All right, so our next step is to plug in this parametrization into the function. So let us copy the function into a blank vector. This, and we have this. Okay, so everywhere that you see x, you plug this in. Because I don't need parentheses there. I should put parentheses here. Okay, everywhere you see y, you plug this in. So there's the y. And that's the only y. Yes. Oh, wait. There's look at the question. There's another y. And everywhere that there is z, it stays z. Okay. So we just simplify that, and we are going to get no change there. This is 9 sine squared u. Okay, so that might be a problem to integrate. We'll see soon enough. That'll be 12 cosine u minus 3 sine. Okay, excellent. So that is our function where we have plugged in our parametrization. Next step, take the partial derivatives. Okay, so here is our function, and let's label. Okay, so this is the r, this is our parametrization. We need ru, r sub u, and we need r sub z. Okay, so we don't get lost. What is the partial derivative with respect to u? Cosine turns into negative sine, sine turns into cosine, z turns into 0. Not 1, but 0. Okay, because that's not a function of u. How about r sub z? Okay, so there is no z there, so that goes to 0. There is no z there, that goes to 0. Derivative of z is 1. Okay, so now we're going to take the cross product. So we want ru cross rz. Okay, so what is the answer going to be? All right, so I'm going to make this scoot a little bit to the right so that we can align them more easily. So this times this, we get 3 cosine u. Okay, so how about for y, we get 0 and then minus this. So minus minus, that's going to be plus 4 sine u. Okay, for z, 0, 0, nice. Okay, that's just going to be 0. Okay, so let's check our answer. Oh, great and all-knowing Maple. What is our cross product? Oops. Sorry. Let's try this. Okay. Yes, there we go. That is correct. Okay, so I will erase that now. Okay, excellent. So that is our cross product. We want to see, are you facing forward? Okay, so check that this normal vector is facing the right direction, the correct direction, which is forward. Okay, the problem said I want forward facing normal vectors. Are you facing forward or facing backwards? All you have to do is plug in a point. Okay, where's the middle of this cylinder? It's at 0. Okay, so plug in u equals 0. All you have to do is plug in 1 point. Okay, so we get 3 cosine 0 is 3. Sine 0, 0, 0 stays 0. Are you facing forward? Yes, you are facing forward. 3, 0, 0. Okay, excellent. And now we are going to take the dot product. Okay, so we have our vector field here with u and z plugged in. Nothing to plug in for z. So we take this and we dot it with our cross product, which is over here. Okay, so one thing to keep in mind, there are so many vectors going on all over the place, and that is why I labeled this. Okay, because you're going to grab things and dot them together and make sure you're dotting the right vectors. Okay, so we're gonna get as our dot product. So yeah, let's make the structure here. We're going to multiply 3 pairs together. So we have this times this. And oh, wait, that's a 0 there. So that third pair goes away. Go away. Sashay away. So there's the second multiplied by 4 sine. Okay, that is our integrand. Okay. So if we're going to integrate this, then what unpleasantness are we going to see? We're going to get 12 cosine squared u z right on. And we're going to get 3 cosine u, right on. And we're going to get 36 sine cubed of u. Yes, and we will get 4z sine of u. Okay, so that is what we're integrating, and yeah, shall we make sure that we are simplified point please. Okay, so 3 cosine u 36. Oh, I'll check it out. They went ahead and did something with the sine cube. Ooh, Maple gave us a hint. Okay, to integrate sine cube u, borrow sine squared u, or separate into sine squared u and the sine u, and then you can do a substitution. Okay, you know what to do. All right, because you could do like really complicated integrals, as I could see from your submissions. Okay, so we're now ready to integrate. Okay, so we will want the integral. Z is going from 2 to 5, if I'm not mistaken. So we have dz on the outside. On the inside, we have negative pi over 2. Keep thinking I'm in GeoGebra. The positive pi over 2. Stop that. D theta. Okay, and our integrand is this thing. Okay, so we know how to do all of that. What's our final answer? Ooh, my. Oh, ha 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 ha. Why did that happen? Because I used the wrong letter. That should be a du, because I used u instead of theta. Okay, so now that's much better. Okay, so that is the flux integral. You're going to use it in physics when you learn about electromagnetic fields. So if you're not going to take physics, I'm sorry, this is not going to be relevant to you. But I hope that you enjoyed the video nevertheless. There's homework for you to do, so it will be relevant in your very near future, maybe not next semester. So until our next video, where we are going to tie up all the different kinds of integrals that we have seen into 3 important theorems. Okay, they're called Green's theorem, Stokes' theorem, and the divergence theorem, which is by Gauss. Okay, so today we are finished with chapter 5, yay! And when we come back, we will begin chapter 6. So until then, I hope you enjoy the rest of your day. Bye!